And yes, what Antonio is saying is true. I mean, as soon as I recruited him as a postdoc, we were blessed with a deluge of papers that he mostly, worked on, and he produced, and not single-handedly, but let's say, 2/3 handedly. Let's put it this way. And then we were able to, I don't know, to create a sort of a small universe to do with distance geometry and proteins. And I think we are still advancing on that. And now we work with the people at Institut Pasteur. So our work that used to be fully theoretical or at least theoretical computational became also applied in the true sense of the word. I'm going to try to sketch some of the theoretical concepts, and then I'm going to talk about atoms and hopefully, if I have time, text and safety distances. But because Antonio is insisting that I do get there, I may skip some of the theoretical parts that he knows better. Okay, so this is, I'm going to suit this talk to Antonio. This talk, of course, is, I'm going to talk about things that I've worked over the years. And so it's joint work with a bunch of people. I put some of the names there, but it doesn't exhaust the list. All right, so this is the table of contents. I'm going to introduce distance geometry and some of the concepts linked to that. And then I'm going to talk about atoms and what changes between the theory that is just abstract and the theory applied to atoms. And then I'm going to talk briefly about text and safety distances. All right, so there's the whole history behind distance geometry that starts before Christ with Heron's theorem, and then it moves to mechanics, and then geometry and topology, and lastly, in the red color, to algebra. I'm not going to have time to go into the details here, but it's a fascinating story. We wrote papers about the history or some facets of the history of distance geometry if you're interested. All right, so let me introduce the distance geometry problem, the main problem in distance geometry. This is an inverse problem, the direct problem, which is very easy. I'm going to tell you what the direct problem is first. You have a bunch of points in Rk, okay, in a Euclidean space with k dimensions, and you have to compute some of the distances between these points. That's it. The easiest possible problem that you might come across. But the inverse problem is that you now have the distances and the adjacencies to the points, but you don't know where the points are. Okay, so you have the adjacencies of the distances to the indices of the points, I should say. So the distance geometry problem has input an integer k and a graph, a weighted graph, where the weights represent the distances. And it asks you to find, or well, if you want to put it into a decision form, it asks you to certify the existence of a mapping between the vertices of the graph, which are index of the points, and the space Rk. And don't forget, k is given. Okay, it's not any k. It's given. It's pre-decided. And the fact that the Euclidean distances should satisfy the distances is given in this system here. It's an algebraic system of degree 2, so multivariate polynomials of degree 2. Now, this is the input together with an index, for example, 2 for the dimensions, the dimensionality, and the existence of this x here corresponds to actually drawing this graph in, well, actually this is 3D, in 3D. And I sketched here 2 possible solutions. We'll see that these solutions are related later on. So a solution of the distance geometry problem, which certifies the existence of this mapping, is called a realization of the graph G. And the word embedding is used more generally. So an embedding may not respect the distances, but it may respect other properties. A realization is an embedding that respects the distances. The complexity of the DGP is a sore point because there is something difficult about the DGP, meaning that these are polynomial equations to be satisfied. So even if your data is wholly rational, maybe these solutions are going to be irrational. Algebraic irrational for certain, but dealing with algebraic numbers is not as easy as dealing with rational numbers. Okay, so it turns out that drawing graphs on a line is the only case where it's easy to see that the DGP in one dimension is actually in NP, in the class NP of non-deterministic polynomially solvable problems. Okay, so why is that? Because don't forget, all of these distances are rational. These are the inputs, okay? So even if you were to find out that one of the points is irrational, you could move it to the closest rational number, and then every other point would move by a rational distance. So if one point is rational, all the other are rationals. And if one point is rational, all the others are irrational. Okay, so the DGP1 is in NP, but what about the other case? We don't know. We think not. Well, I think not, because I made some computational experiments here with a few representations, known representations for polynomial solutions. And I could always find a counterexample to the conjecture of being in NP. But of course, I didn't exhaust the possible representations. That would be a difficult feat. I talked about this problem with many people, and Alexander Barvenok once told me that it's obviously not in NP. And then when I pressed him for details, he said, no, maybe it's not that obvious. But then he said, no, but I can prove it. But they never sent the proof. So I don't know. I trust the guy, but I don't have the proof. And then Gabor Pataki in the last workshop at this semester at the Fields Institute talked about having polynomial certificates for the SDP feasibility problem, which has the same issue as the DGP, but it's not the same as the DGP. So I don't know whether his methods can be moved over, and I don't even know whether, I don't think that he actually closed the problem of the SDP feasibility either. So there's a sign that maybe there are ways to think about this, but it's not settled. So as long as we don't know whether it's in NP, we say it's not in NP, all right? So the DGP is actually NP hard, meaning that there is a reduction from partition, which is a weakly NP hard problem, to the DGP, which is easy. And then there's another reduction from the same paper by Sachs in 1979, which proves that it's actually strongly NP hard, even when the weights are just 1 and 2. Okay, and the reduction here is more complicated. There's a gadget, but it's from 3 sat. There are also polynomial cases, like, for example, complete graphs, and we'll see later why they are polynomial cases. And when I say polynomial cases, I mean that an accurate solution can be found in polynomial time, maybe not a precise solution, because maybe we cannot represent it, okay? But let's say epsilon close. All right, so the instances of the DGP may lead to a set of solutions called big X here that has no elements, in which case we say that the instance is infeasible. It's a no instance. Or maybe it has finitely many solutions, in which case we say that the graph is rigid. If it has only one solution, then the graph is globally rigid. And if it has continuously many solutions, then the graph is flexible. And I want to remark that it's impossible to have an countable number of countably infinite number of solutions, and the impossibility follows by a theorem of Milnor, which puts an upper bound to the number of connected components that any manifold can have, or any subset, any solution of a polynomial system can have in a Euclidean space. Okay, so because of the number of connected components is finite, you cannot have an accountably infinite set of solutions here. So here we see an example. This triangle, wherever you draw it, unless it's on the line, but from the plane onwards, it has one solution on the line as well, in fact. Then this graph that comes realized here is 2 incongruent solutions. One is this one that I circled, and the other is this one here. I can reflect X4 down here and obtain another solution, because you can see that I don't have an edge between 3 and 4. So it doesn't, this distance is not given. And then you have certain graphs like this one, where you can continuously deform the graph, well, the realization of the graph, and you obtain an uncountable manifold. Okay, so you have an uncountable set of different realizations that are all valid realizations of the same graph. So let's see how we can solve this problem, or at least let's see the basic block that we can use to solve some instances of this problem. And these blocks are called k-lateration. So let me show you what 2-lateration in R1 is like. This is the graph, okay? And you can see that the given distances are 1, 1, and 2, which means that they just barely satisfy the triangular inequality at equality, okay? And if we realize it on the line, this is useful because that gives us a realization that can fit on the line, okay? Like, how do we do this algebraically? Well, we have two equations, okay, that define this problem, supposing that at least these two vertices are already known, okay? So suppose that you've already somehow guessed the right position, the correct position for these two vertices, and then all that's left to do is to decide the position of the vertex 3, okay? And these are the two equations that we need to satisfy, okay? So you write the equation in explicit form like this, and in red you will see the variable that we need to determine, whereas in black you see the data, meaning that you know x1 and x2 already, so x1 here and x2 here, they are known, okay? So now if I subtract the first equation from the second, I end up with a linear system because the two squares here disappear, okay? And this linear system reduces to this form here, whereby I can easily compute that x3 is equal to 2, okay? Now, the generalization of this operation of 2-lateration leads to a k-lateration, whereby you can embed or realize a k+1 clique in R to the k-1, okay? So k-lateration can be used in this sense when you solve a single linear system and you're done, when you have k+1 vertices with positions that are already known in R k-1, okay? All right, so this leads to a k-1 times k-1 system of this form, which can then solve. So this is what happens when you generalize the slide that I just showed you. You can assume that x1 to xk are given in rk-1, and you want to compute xk+1, okay? And again, like I explained before, you draw up the k-quadratic equations that you must satisfy in order to have your DGP instance be yes. They are all in k-1 variables. And then you see that they're all quadratics, but if you can take the last one, for example, and subtract the first, the second, etc., from the last, and then you can obtain k-1 constraints derived from this system here, where everywhere the quadratic terms disappear, okay? And so what you're left with is a linear system of this with this shape. This is a k-1 times k-1 linear system, which you can solve, and as long as it's got full rank, it may lead to infeasibility or wrong solutions in the sense that whereas the quadratic systems imply the corresponding linear systems, the opposite does not hold. So either this may happen to be infeasible and then the instance is no, or whenever it's feasible and you obtain a solution y for the k+1 vertex, you need to plug it back into the quadratic system to verify that it's correct, okay? All right, so the natural embedding dimension for a k+1 clique, however, is not rk-1, okay? So if you have a triangle, only a very special triangle will fit on a line. If k is 2, you have 3 vertices on the triangle and 1 dimension in the line, okay? But in fact, if you have a generic triangle, you need 2 dimensions. So the natural embedding dimension for k+1 cliques is rk. So what happens if you apply what I just described to rk instead of rk-1 is you get a system which is rank deficient, k-1 times k, all right? So now what you can do to solve it is that you can partition the columns as basics and non-basics, okay? And you can assume that the non-basics is just one column because the rank, if these matrix is full rank, A has full rank, then it's got rank k minus 1. So there's only one non-basic column that you can choose. Well, so you can choose multiple non-basic columns, but the set n always includes one element, okay? The set big N. So this is now the form of the system, and you can, of course, transform it in this way. And then you can move, you can express the basics in terms of one non-basic variable, which you can now use, this equation you can now use in one of the quadratic constraints. It doesn't matter which one. So we'll use this one here. You can plug in into Y, you can plug in, instead of YB, the indices in the set B, this expression, which is only expressed in terms of a single variable n, okay? So you get one quadratic equation in one variable, which you can solve, and you can get either 0 or 1 or 2 solutions, okay? And then you can, with that value, you can compute the other components of Y. So K-lateration can also be used in RK. And we can exploit K-lateration to define two types of algorithms for solving certain classes of distance geometry problems, but these classes are nice, okay? They're interesting. The point is we want to iterate K-lateration. If you're given a good vertex order on a given graph, i.e. one where the ith vertex is adjacent to at least K predecessors in the order, then K-lateration in Rk minus 1 leads to at most one solution or none, and K-lateration in Rk leads to no solutions or one solution or two solutions, okay? So in the case of K minus 1, this would be the situation, okay? Somehow your clique, the Rk plus 1 clique, is flat, okay? This is a tetrahedron that just happens to be flat, like the example of a triangle that used to be on a line, okay? This is a tetrahedron that is flat. And so basically it's the same situation as if your quadratic equation here only gave two solutions that were superimposed, okay? So effectively, it's the same as if in K-lateration for Rk, the two solutions were only just one. Whereas in Rk in general, you can have two solutions, and this is the picture that you see. They are reflections of each other over one of the faces of the clique, okay? So now, if we iterate K-laterations in Rk minus 1, we get a polytime algorithm, because at each iteration we get at most one solution, okay? Whereas if we iterate K-lateration in Rk, we get at most two solutions, which leads to an exponential algorithm in the worst case. The polytime algorithm is called geometric buildup, and the exponential algorithm is called branch and prune. There's one outstanding point, however, the system rank. If A is rank deficient, many things can happen, but let's see the simplest rank deficiency, where two rows of A depend on the others. In both cases that I depicted here, for K equals 3 and K equals 4, you can see that a circle is involved here, okay? So the locus of R of xk ends up being not in one single position or in two positions, but in uncountably many positions, okay? And in fact, there's a theorem by Hendrickson that says that if a graph G is connected, flexible, and has more than k vertices, then the solution set will contain almost always a submanifold diffeomorphic to a circle. So we can't identify a finite number of positions for the next vertex, and the algorithmic background sort of disappears, or at least this iterative background disappears. By the way, Hendrickson theorem does not just apply to cliques. We can see here a graph that was in Hendrickson paper where there's a flexibility, and the flexibility applies to this triangle, okay? So this triangle itself is rigid, but it's linked flexibly. And if you turn this triangle, you can see how the vertices start turning. And then this thing sort of, the triangle revolves, but this triangle also turns on itself. And what happens is this situation. And if you go on, you will see that the center of mass, or at least one point in the triangle, will design a manifold similar to a diffeomorphic to a circle. All right, so let's see the geometric build-up algorithm. This is the algorithm given is in recursive form. So the recursion starts by passing the k+1 vertex index and an initial realization for x1 to xk. And then for when we are now at level v, okay, at the vth vertex greater than k, we assume that we have a partial realization x bar that goes up to xv minus 1. So we use k iteration to compute a set of solutions of at most one positions for xv. And then for each member of this set S, which may be either 0 or 1, okay, at worst, we have to stop because there's nothing that we don't find the next vertex, or maybe we just repeat this loop just once. We have to check that it's that the position that we found is compatible with all of the previous adjacencies, and if it is, then we can lengthen x bar, extend it so that it also extends to v. Okay, and if v is equal to n, that means that we've realized all of the vertices, so we can return the realization. Otherwise, we need to call GBU again on the index v+1 with x as the initial vertex. Now, the prerequisite here, the vertices are ordered so that the k-iteration is possible, which for k equals 3, for example, v must be adjacent to 4 predecessors. Okay, so it requires a certain density of the graph, which may be problematic for applications, as we'll see later. The other thing is that this algorithm finds at most a single realization, but of course it finds a realization with respect to the first given vertices. Okay, so you give the algorithm these positions, and then it proves that there is a single realization, or it proves that there is no realization given those positions. It may happen that if you pick the wrong initial k positions, you end up with a no answer, even if the instance is yes, and then you maybe have to change these k positions and start again. Okay, so in order to find other realizations, you may vary the vertex order, okay, and especially the first k part, the k elements of the vertex order. All right, so the BP algorithm is almost the same. All right, so you can see some of the differences here. Instead of at most 1 positions from k iteration, now we get at most 2 positions from k iterations in step 2. And now the loop can be executed 0 times, 1 time, or twice. Instead of, if v is equal to n, instead of returning, you have to add the full realization to the set of solutions big X, and then continue, because you may have other open nodes here, or else call. In fact, there's another recursive call here, but it's not recursive. You have to sort of restart BP. Okay, so restart BP with different things. Okay, so anyway, so here, otherwise, if you're not at n, then you have to call BP recursively on like you did for the geometric build-up algorithm. And here the prerequisites are weaker because now a k iteration in RK needs fewer adjacent predecessors. So in particular, in 3 dimensions, you need 3 predecessors, and that means that you can apply it in more cases, to more applications. By the way, branch and prune finds all realizations and given the first k vertices, and it finds incongruent realizations as well. So that's an important property of branch and prune, this completeness, this way of finding all solutions given the first k vertices. And of course, it can be easily modified to find only p solutions if you just need p of them, because you can stop as soon as the cardinality of x becomes p. All right, so in comparison, the important point is density. Okay, GBU requires denser graphs, whereas branch and prune requires sparse. It can work with sparse graphs. There's also Other points of comparison, well, of course, a GBU runs in polytime, as I said, whereas at worst, branch and pruning is exponential. But one nice thing, one nice property is that branch and prune, we found it to be very fast in practice. And then later, we found that for many interesting application cases, the branch and prune algorithm was fixed parameter tractable. The proof is not easy, so I'm not going to sketch it here, but all tested prototype backbones, for example, had a low parameter value, and it's easy to see that, well, once the proof is given, it's not hard to see that if protein backbones are alpha helices, then this is linear time, okay, which also explains the empirical speed that we found. All right, so let me introduce briefly mathematical programming, just in case there's anyone. Well, actually, maybe all of you here know mathematical programming. Maybe I can, let me see some of the names. I don't know. Maybe I don't know everyone. I don't know. Anyway, so mathematical programming, easily done. Very short introduction. This is a declarative formal language for optimization. The valid sentences are called formulations. They describe optimization problems. And these F and G I's that describe the objective function and the constraints, they are written in expression language, so they're not just anything, but they have to be written down. They have to have a closed form formulations, a closed form formula. Each of these formulations, these sentences of the language, can be interpreted by a solver that gives you the semantic of the sentence, which is actually the status of the problem, meaning whether it's bounded, unbounded, feasible, infeasible, optimal, or not. If it is optimal, then you also get given a certificate of optimality, which is usually called the solution of the problem. Okay, so these interpreters are, I call them interpreters in the framework of formal languages, but they are solvers for given subclasses of mathematical programs. For example, there's a simplex algorithm for linear programming or interior point methods for other classes of mathematical programs. Let me see the chat. So round off is a problem, but I'm sorry. So there's been, okay, so thank you everyone who's answering questions instead of me, so I can go on with the talk, and maybe we'll leave the discussion later. So you can see here names of classes of mathematical programs. Here we are mostly concerned with QP or NLP, SDP. Okay, so but at the end of the talk, I may get to a bi-level programming and semi-infinite programming. The nice thing about mathematical programming is that it dispenses you from finding a solution algorithm. Okay, so just formulate the problem and then call the solver and you're done, which I find very useful. So for the distance geometry problem, there are several possible mathematical programming formulations, quadratic equations. So this is a feasibility only quadratic program, and it's not easy to solve. Most solvers will give up on this, but you can easily reformulate it in a way that solvers like, meaning that you make the system easier to satisfy by adding slack variables, and then you minimize the sum of the square of these slack variables, so that you aim at optimizing, you may aim at satisfying the quadratic constraints. Okay, so this is useful, and this slide tells you that in mathematical programming way of thinking, if you will, it's also easy to solve, because you just write down the formulation, okay, which is actually very easy to the mathematical program that I sketched in the previous slide, and then you call the solver. That's it. That's what you do. You give it some data, for example, this protein here, and then you find a realization of the protein. Other formulations are possible. For example, here I'm showing an unconstrained global optimization one. This is nice because there are no constraints. On the other hand, it's not that nice because it's not quadratic, but it's quartic. There's a square here and there's a square here. And in particular, it's not convex. It's not convex in XU and XV. Let me just say that XU and XV are vectors here. They're not scalars, okay? However, this can be reformulated exactly, meaning that the optima don't change to this form with the L1 norm instead of the L2 norm there. This is still 2 and this is still 2. I'm talking just about the error terms. And if you can further reformulate this to this form. Now, this is quadratic here, but concave because it's a maximization problem, but it's got convex constraints. So this is actually quite an interesting formulation to use in practice. It can also be used to draw up an SDP relaxation. In particular, you can rewrite these terms to this form, the blue one. That's just very easy. And then every time you see a nonlinear term like this one, and that one, you replace it by a new added variable, okay? And you can see that because each of these nonlinear terms is in fact of this form, this is just like twice xi, I equals j. You can index all of these added variables with two indices, okay? So it's a matrix of decision variables. So x, this is the linearization of this nonlinear constraint, but you also need to remember that xij is equal to xi times xj, or scalar product xj, for every I and j, and this is a compact way to write it. Okay, so this is a reformulation so far. No difficulty has been removed yet, but the relaxation is as follows. Instead of saying that x minus xx transpose is the zero matrix and hence also only has zero eigenvalues, you are requiring that the eigenvalues of this matrix are just non-negative, okay? So this is now a relaxation that can be written in this fashion, but if the small x's don't appear in the original formulation, in the relaxation, like here you see no small x's because we relaxed that, then you can, instead of writing the Shor complement, you can simply write x is positive semi-definite. All right, so this deals with constraints, but we still have a possibility to choose a function, an objective function. It must be linear, of course, in the matrix variables, and I'm suggesting that we use this linearization. So the linearization of this objective is this objective function here, and it requires you to change this less than or equal, like it was here. And this is quite a good objective function for protein applications, as we'll see later. Also, other objective functions have been proposed in the literature, like, for example, minimizing the trace. And it makes sense because it tries to minimize the rank, but it doesn't always work. I found that adding some term, small term times the trace of x yields a very good objective function for proteins. There's also a suggestion by Barvin to just use random f's, and there are deep theoretical reasons why this should work well. And I tested it, it does actually work quite well. All right, so let's look at what happens later, because now we can solve an SDP. Why are we interested in solving SDPs? Because the reason is that we can do this in polynomial time up to a given epsilon accuracy, okay? So solving an SDP is more similar to solving NLP than solving a non-convex NLP, okay? It's easier, let's say, tractable, okay? But the solution is an n times n matrix, and the rank is usually not the rank you want. So you'd like rank k. This k is given in the DGP, but in fact you get a rank r, which may be close to n or a little little smaller, but not rk as desired usually. Okay, so you have to do some heuristic movements, some heuristic things in order to get rid of the unwanted multiplicity of rank. So two things that I suggest to do is apply principal component analysis. So get rid of the eigenvalues that are non-zero beyond the kth one, okay? Or apply this very easy Barvinox naive algorithm, which I think is very interesting because you just need to sample a random vector from this distribution component-wise that has the correct dimensionality, and then you take a factor from the solution and you just multiply by the random vector, and you get something which is close. Okay, so both methods define, we'll find some x bar in the correct dimension, which are close to big X bar. Okay, having gotten this, you can now find the local optimum using one of the many local NLP solvers from a given starting point. So all of this is functional to computing a starting point to a local NLP solver, which will usually give you quite a good solution X star. All right, so let's look at atoms. The molecular structure from distance data is the reason, the motivating application for studying the DGP. Okay, so the vertices of the graph are the atoms of the molecule. K is obviously equal to 3. An edge is in the graph if the distance between the two adjacent atoms is known. Okay, the distance values can either be inferred from chemical considerations. For example, covalent bond lengths are known fairly precisely, or can be estimated by nuclear magnetic resonance up to 5.5 angstrom. So this, in theory, gives you a graph. Now, this is not the whole truth. I'll tell you later why it's not the whole truth, but it gives you a graph, and it doesn't give you a realization. So why not use X-ray crystallography that really does give you a realization directly? It's because sometimes you cannot get a protein to crystallize, and so you can't employ that technique. There are also other techniques, more modern techniques, that give you a realization directly, like cryo-EM, but NMR is still used. All right, so what happens in practice? Well, first of all, proteins are formed by a backbone plus side chains. And whereas there's a natural order on the backbone that we can hope to use perhaps because we need a vertex order in order to apply these distance geometry methods, there's also the side chains, which don't naturally have an order, and also the backbone plus the side chains doesn't have an order naturally, okay? So what you can do is you can realize the backbone first and then try to stick the side chains on. If it doesn't work, change the solution in the backbone and go on. Okay, so there's a certain decomposability between backbone and side chains that we're going to exploit. Secondly, protein graphs have errors, okay? So some are experimental. For example, you can't really measure a distance precisely, so you have an interval, a fairly small interval. But otherwise, there's also systematic errors, meaning that, in fact, the reconstruction of the graph from the actual NMR outputs is prone to errors, meaning that there's a symbolic post-processing that does something that is 95% correct, but 5% is wrong. So some of the edges in your protein graph really shouldn't be there, and some of the non-edges, some of the pairs that don't have an edge, really should have an edge. So some of the graphs are really misplaced, okay? So this is pretty serious. Of course, the natural backbone order may not satisfy our GBU or BP assumptions. And there's also the limitation that NMR is most accurate on distances between hydrogens more than other types of atoms. Moreover, the realizations from DGP do not consider energy, but it's known that when proteins fold, they follow a path to a minimal energy. So let's see how can we address some of these issues. First of all, I told you there's a certain decomposability of backbone and side chains, so let's just limit ourselves to backbones. And secondly, actually side chains have orders, meaning that Antonio and some co-authors have defined orders for each of the, I don't remember, 20 amino acids that are commonly found in proteins. So we now have orders for all of these that respect the assumptions demanded by the branch and prune algorithm. Let's come to the experimental errors. I said that the covalent bond lengths were known precisely. Well, let's assume they are known precisely, although this is not exactly right. That means that subsequent atoms in the order, so the order here would be C, B. I don't know if you can see this. I can maybe make it small, larger. So the order would be C, B, A, and then I. Okay, so you can see that there are two positions of I, but this is the order. Okay, so that's the order. CDB is a covalent bond. CBA is a covalent bond. Oh, sorry. CB is a covalent bond, BA is a covalent bond, and AI is a covalent bond. So these distances, DCB, DBA, DAI, are known precisely. That we also know that the covalent angles are known precisely, and this is further from the truth than this precision here. Let's say that these are assumed to be unit in most cases, and deviating from this sort of assumption is a costly exercise that we're looking at, but this is not necessarily something that people master very well. Okay, but so let's assume that if not unit, at least we have a value for these angles, or a few values for these angles. Okay, so now we can compute from all these distances and the angles between them anything we want about the triangles CBA and BAI. All right. In particular, we can compute the length of the third side fairly precisely. All right. So we know CB, CA, BA, BI precisely. But what we're missing in order to be able to apply branch and prune would be CI. Okay. So we need that too. So usually CI is small enough, this distance in red is small enough so that it can be estimated by nuclear magnetic resonance, but as an interval. So this is really an interval. It's not like this precisely in inverted commas. This is a fairly large interval. Okay, so you really have to treat it as an interval. So far we've discretized it, and of course this ruins the exactness completion of branch and prune, but it does give some results. Carlile and some other co-authors have worked also at describing these curved intervals. These are curved intervals in the sense that they are intervals of a circle, giving explicit equations that describe these intervals in space using Clifford algebra. Gave some results, but it's not yet ready for prime time. So what about vertex orders? We've studied these exhaustively, and we think we've now sort of mastered what we need. So orders are now well understood in abstract terms, and when we apply them to proteins, we have to keep in mind that we should really just use hydrogens. So if we want to just use hydrogens, we have to somehow define orders in a special way. And these special orders pass over the same atom multiple times. Okay, so they are repeated orders. Now, Carlile was able to handcraft these repeated vertex orders for protein backbones, and then Antonio extended this definition to all of the side chains. But it's also now known that we can find such repeated orders automatically in polynomial time. So in certain cases, of course, I mean, not in general, there are some assumptions for the BP, etc., etc. But at least we can do this algorithmically as well. Now, the systematic errors, we don't quite know how to deal with them yet. But let me just tell you what they are, where they arise and why they arise. NMR actually doesn't produce a graph, but a probability distribution over pairs. Okay, so in coarse terms, these pairs are atom types. So it can NMR can tell you that maybe the triplet HH 3.5 angstrom happens with a certain probability, which means that there's a certain probability of finding pairs of hydrogens that are at 3.5 angstrom from each other. Okay, this is a kind of output in coarse terms of NMR. Okay, more precisely, it's not just hydrogens. Maybe there are some of the hydrogens. So more precisely, you can define subsets of protein atoms, but not single atoms. And then you can have a frequency of finding a certain distance over these subsets. Okay, and the probability is actually proportional, or it's believed to be proportional to the distance value. Reasonably proportional, let's say. Okay, so from this output, there's a machinery behind, a computational machinery behind the chemical NMR machine that does some post-processing, and this post-processing leads to a protein graph. This post-processing has been done for a long time using simulated annealing. We haven't really managed to get in touch with many people who deal with this side of NMR. They're usually most concerned about the chemistry, and they don't care a lot about the computational side, so it's difficult to convince them to spend time and attention about the improvement of a simulated annealing paradigm, okay, or maybe just change it and define a combinatorial problem instead. On the other hand, that's what they do, and that leads to it's an effective heuristic. It's used to solve an assignment problem between distance values and the actual atoms they correspond to, okay? But of course, this heuristic makes mistakes, and so some 5% on average of the edges are misassigned, and this is why the systematic errors. So the simulated annealing actually works by minimizing the energy, or at least an energy field that is believed to be active in proteins, and so this is where the energy comes in. After talking extensively with 2 people from Institut Pasteur, that's my understanding of the actual problem that I should be solving, or that we should be solving, but it looks very, very difficult. It looks challenging, very challenging. Okay, so there's a set of subsets of vertices that may not even form a cover for V, and these subsets are what I use to generalize the coarse interpretation of pairs of hydrogens. Okay, so instead of IP in coarse terms, you could read hydrogens, carbons, oxygens, or whatever. Okay, and then these edges of the graph are between atoms of one type and atoms of another type. Okay, in this subset of sets of vertices, whereas these other edges B are the edges where the covalent bonds are known precisely, so the covalent distances are known precisely. NMR gives you a density over pairs IP, IQ contained in some range, okay? So the density is not a precise density either. It's just like an interval density, all right? So the protein conformation problem is to solve this system of equations and inequalities. This is the usual system, but the distances are no longer given. The distances are also decision variables, and they have to satisfy these inequalities where these beta are given, and I don't know exactly how they're computed, but apparently they're not. Okay, so this 1 over d to the 6th is an energy term that might remind some of you about oh my god, I forgot the names of those clusters. Well, never mind. Anyway, so it's an energy term. So this is private communication, so it stands to criticism. It may not be the best model. Certainly does not look like an easy model to solve, but that's what that's where we're at. But even with the machinery, the approximate machinery that we've concerted with our colleagues at Institut Pasteur, we managed to produce some results on real proteins, of which I'm very proud. Now let's go to text. We know that relational knowledge in general, okay, forget proteins, is best represented by graphs, okay? But we have fast algorithms for clustering vectors and for doing machine learning on vectors. So if you want to do machine learning on graph, there are some methods, but it's not ideal, okay? So the task that comes up repeatedly is to how to represent a graph as a vector in a Euclidean space. And this is used heavily in images, moving images, sound, and also natural language processing. We obtain word vectors and concept or sentence vectors. Now let's see. This slide sort of is supposed to give you an idea of what's going on in those terms in natural language processing. This is the projection of a word vector set in 2 dimensions. Okay, so you can see that the points are represented by words, or they represent words, and this is 0. The 0 is probably here in the center, and I don't know, fried would be this vector here. Okay, the word fried, I mean. Once you have these vectors, I'm not saying how we can do them yet, we can produce them yet, okay? But once you have these vectors, you can do clustering on vectors, and you can find out that, for example, related things are in a sort of zone, okay? And this is a very optimistic outcome, but it may happen, or let's say that in 2D, it's not always very easy to see this, but in multiple dimensions, it it may happen. It's not clear cut, but it does actually happen. And then there is a very much celebrated conjecture called the analogous conjecture for word vectors. So the analogies say that if you have pairs of related words, for example, man, king, and woman, queen, the difference vectors between the word vectors for queen and king, or for woman and man, these different vectors are almost parallel, okay? And the analogies could be either semantic or syntactical, like this one, and it should still hold. Moreover, by transitivity, you should have that multiple analogies also yield almost parallel difference vectors. Well, we found that this is not quite the case, meaning that this analogies conjectures is useful to convince people to use word embeddings, and sometimes it does apply, okay? But it's neither algorithmically exploitable, nor is it really true in any sense of the word, meaning that there are many quadruplets of analogical words that yield different vectors, the difference vectors that are not parallel, and there are many quadruplets of non-analogical words that yield difference vectors that are almost parallel. So sometimes it holds, sometimes it doesn't, but you shouldn't read too much into it. Now, other properties of some word vectors, or other desirable properties that should lead to, you should guide the construction of good word vectors, would be the identification of some semantic axis, for example. Here we can see that anything small is on a side and anything big is on another side of one line. Okay, so that would be nice. Again, it's not always the case, and there are infinitely many semantic axes, so it doesn't seem like an easy constraint to impose during the construction of a word vector set. More complicated things, yes?
I'm sorry to interrupt you. We have other 5 minutes in total. One thing we could do is to continue until the end of the time slot, and then the people will ask you questions during the coffee.
Oh, because there's no time for questions apart from the. Oh, I'm so sorry. I didn't realize this. Okay, no. Let me just finish here. I think I said enough. I want to answer 5 minutes of question. Now, if no one has a question, then I will retreat.
There are questions, I think. Yeah, please.
All right.
Leo, you wanted to conclude?
So there are no questions? Okay. All right. Yeah. So if there are no questions, then
there were questions in the chat.
In the chat. Okay. So, and I've lost the chat. I'm not so. I've been using this tool so much, and I still cannot deal with it. Okay. So there were questions in the chat. Let's see. What about round-off error build-up in Ecole iteration? Yes, it's bad. It grows. It's we found
actually, and I should have added the word Nathan mentioned also, that of course when there's noise to begin with.
Yeah, but
if there's no noise, if everything's clean, then maybe it's okay. But
so the way I described Ecole iteration, it is very ill-behaved with respect to noise. Okay, so it's not a good way to do Ecole iteration. But if you know that your dimension, meaning, for example, it's 2-dimension or 3-dimension, is not going to change, then you can replace Ecole iteration by combinatorial algorithms that are more efficient than solving, more precise also than solving a linear system, which means that in practice we can get away with applications. So for atoms, for example, we have a branch and prune that is fairly robust. But I'm not very happy, meaning that the kind of noise that we get in atoms still exceeds the precision that can be maintained by the best algorithm. Okay, so yes, this would be my answer.
Are there other questions from the audience?
Yes.
Please.
Can I ask a question?
Yeah.
So I was at the end of my PhD. I worked on a paper. Henry and I worked on a paper with Babak Ali Panahi, and part of his PhD dissertation dealt with this problem of assigning the distances to based on NMR data.
Mm-hmm.
And I was wondering if you were familiar with this work, or, I mean, it's quite old now. It's from 2011, so I don't know if things have really
No, I'm not.
improved since then.
If you
But
could send me, Nathan, if you could send me a link, I'd be very happy to look at it. I don't
okay,
know if in fact, I don't remember whether I'm familiar with it or not. It's been a
yeah,
while since I last looked at it, but please send me the link, okay? I'll check it out.
sure. Yeah, I'll send you a link to our
Thank you.
paper, and then I'll see if I can find his PhD dissertation as well.
Right,
Um,
good.
one thing that we ended up doing in that paper was we considered the issue of some distances being like assigned incorrectly.
Mm-hmm.
And so we did sort of like a L1 minimization penalty on some the slack variables, or so we had some additional slack variables, which we wanted a small number of them to be non-zero, but we wanted most of them to be zero. And so that's how we handled this possible like completely incorrect distances.
Right.
And that was part of the SDP model.
But still, I think that you still lose the optimality in this sense. Maybe the real protein, maybe your optimum would be feasible optimum and even better than the real protein. Maybe the real protein wouldn't be optimum with respect to all of the objective function that also optimizes over these kind of errors.
Right,
because it depends also on the experimental errors, meaning that if the intervals are a little large, if you miscalculated the bond angles, I mean, there's so many things that can go wrong in practice that I'm certainly interested in anything that, that works in that direction. But I don't think that it's really something that you can solve completely. Okay, so this is a failure in the given data. So it's wrong input is difficult to correct. I mean, it would be interesting perhaps to decide in which cases, for which graphs and for which errors, the optimum of, for example, your objective function actually describes the optimum, the real protein. Yeah, that could be, give bounds to any method that you think to correct this data, to what extent they can work. Yeah.
Okay, I'll send you some of those links. Yeah, thank you, Leo.
We have time for.
So I think I exceeded my time.
Yeah, okay, but we can. We have a large coffee break after Phil, so I think we can. If there are the questions, we can still.
Okay.
Are there questions from the audience? Yeah, okay. There would be my question about the safety distances. But I don't know if you can answer in 1 minute. It's too long.
Well, maybe.
Just to give the idea.
What's your question?
The safety distances.
That's not a question.
Yeah, okay. Yeah, I know. But but what about it? What
right, so okay, so I'll show you the slide for safety distances, okay? Here we go. So you have a set of flying vehicles information, and they must cross paths without collisions, okay? So the safety distance is enforced like this, obviously, but every one of these flying vehicles, they fly, and so they change their position. So now you have a problem that depends on an infinite, an uncountable number of indices, if you will. And this is the formulation of the problem, okay? So you're trying to change speed as little as possible within some bounds, and you are computing the next, but it's not really next because this t moves continuously, okay? The next position of all the flying vehicles, and every pair must be at distance d, okay? The safety distance. This is a semi-infinite problem, and it's quite difficult to solve. Fortunately, there's a range of techniques for dealing with this. The first one is the reformulation to a bi-level program. So instead of saying, I want for every t in the interval this constraint to be satisfied, you can just want it for a minimum distance, okay? So the time that defines the minimum distance, okay, between two flying objects I and j, at that time you want to enforce the constraint, okay? So now this again is a bi-level programming problem. It's not easy to solve, but there are some single level reformulations that because this second level problem is actually convex. Okay, so this is not part of the problem. The second level problem is actually this one. So it's a minimization of a convex form. Okay, and then the value of the optimal value of the second level problem needs to be bounded below. Okay, but this corresponds to a convex lower level problem. Okay, therefore the KKT conditions or any dual, like for example Wolf's dual or Dorn's dual, they give you three different single level formulations that are non-convex. Unfortunately, you can see here this equation. This is a decision variable, this is a decision variable, this is a decision variable, wait a second, this is squared, right? So everything is squared here, and it appears on the wrong side of this, and so this is a non-convex problem. Okay, so you can try and solve it, but it's still challenging. This is a new formulation, new singular level formulation that uses a method similar to Lasserre's hierarchies, but it's simpler because we are now we just have squared polynomials here. We don't have polynomials of general degree D, so we don't need all that complexity. There's a lemma in this paper that just deals with the case we want, and so if we apply it to the semi-infinite constraints directly, we get this polynomial, and then we get this certificate in terms of sum of squares. That the required constraints hold for any t. Okay, and you can see t is not part of the problem here, but this is the beauty of Lasserre's hierarchy, and let's say sum of squares reasoning is that it gets rid of the continuous variables in some cases. Anyway, so it leads to a non-convex QP, but which is smaller and more effective to solve than the other single level reformulations.